if you need to transport a lot of current, like kiloamps of current, then a thin little wire often won't do because it'll heat up too much with large currents. So instead, what you might use is a solid slab of metal called an electric bus bar, just like a solid chunk of copper that you would run current through along the surface and coming out through the cross section here. Viewed from the side, our bus bar or electric bus would look like this with our current coming out through that cross section. And knowing what we know about the shape of fields created by individual wires and by the solenoid, we can predict that right-hand rule, thumb in the direction of that current. This slab carrying current out of the page will be generating magnetic field in the surrounding environment. And those field lines probably look like this, circulating that way. Further out line, maybe something kind of like that. B fields around a current carrying bus. Okay, so let's study the B fields in a system like this. You might find a system like that, a bus in, say, like an electric substation or in heavy industry, places where you need to, transport kiloamps of power, of current. Okay, so we can study this best if we consider the ideal case, the case of the infinite bus, the infinitely long, infinitely wide solid slab of conducting material with some uniform current density distributed throughout its interior. So here's our cross section. We've got this current coming out of the page everywhere through that cross section. We'll give this piece of metal a width W, but it extends infinitely to the left and to the right. Okay, we'll use Ampere's law to investigate what the B field might be like around the environment around this infinite distribution of current. We'll start with an Amperian loop, a rectangular loop over here that goes both above and below the slab. And let's say that we're going to circulate this way around that loop. Okay, applying Ampere's law, we will have on the left-hand side of the law a contribution from this segment here. Let's call that B dot ds along the, we'll call it the bottom segment of our loop, of our Amperian loop. Then up this segment, we know from the symmetry that we're going to get ds and b perpendicular to each other. B will be only horizontal here. B will be looking like it's pointing to the left above and pointing to the right below. And likewise, we'll get that same thing inside here as well. So b dot ds will be 0 along that branch, and b dot ds will be 0 along this branch. So plus 0 for those branches. Then up here, b will be to the right in the direction of ds. So we'll get a contribution b dot ds along that top branch. Then b dot ds will be 0 along that side branch, equals mu naught times our current enclosed. The current enclosed, the current sort of passing through this open surface here, bounded by our rectangular Amperian loop. Okay, so by symmetry then, B should be uniform across this bottom segment, and B should be uniform across the top segment, although B at the bottom might be different from B at the top. So these two open line integrals will simplify. Let's call the length, that length right there of our Amperian loop, let's call that L. And note that we're expecting B to be parallel to ds up top and B to be parallel to ds down below. Let's call that B top and B bottom at those two different locations. So B is uniform along each of those segments, and it comes out of the integral, and the sum of the dS's is just L, so this becomes B at the bottom times L plus 0 plus B at the top times L plus 0. Okay, B was in the direction of ds below and above, so we know that these are not opposite in sign in this case, based on this picture. So these are both going to be positive terms. We are definitely enclosing some current here, so we have a non-zero right-hand side as well. The current enclosed should be equal to our uniform current density times the area of the slab that is actually contained inside our Amperian loop. So J times this area here, the area through which current is actually emerging. There is no current coming through this part up here, no current coming through this little part down here. There's just current coming through this square right there. And that square has area little l times width w. So J, L, W, that's the current enclosed inside this rectangle right here. Okay, so I think that's all we can learn from this particular loop. We've got a non-zero B at the bottom or the top. And by symmetry, it can't be 0 here because that would imply there would be 0 somewhere up here. So it looks like we have non-zero B at top and at bottom, but like we still want to know how big that B is on top and bottom. So next loop to consider. Let's draw one, say here. That encloses some of the current, or some of the current in our slab. And next to that one, a loop with the same width that encloses the same amount of current. So same length L here and here, and enclosing the same amount of current there and there. By comparing these two loops, and looking at our equation here, B dot ds along the bottom segment should be the same for both. The current enclosed should be the same for both, which implies that B dot ds along the top segment should be the same for both. And since L is the same for both, what we're concluding here is that the magnetic field along the top segment must be the same at both of these locations. Therefore, we're finding that B does not depend on your distance above the slab. And we concluded earlier that B is also non-zero everywhere above, well, at least some places above the slab. So I think what we're finding here is that we have a non-zero magnetic field above and by symmetry below our slab, and moreover it is non-zero and uniform. Same B value at this location and at that location. Down here we're finding that B at the bottom must in fact be equal to B at the top. Okay, so apparently with this infinite slab, it's creating a magnetic field that extends all the way to infinity and is non-zero above and non-zero below. Non-zero and uniform. Okay, let's find an expression for the strength of that. I think we can continue to use this equation right here. If B at the bottom is the same as B at the top, then that equation can be rewritten as 2 times B times L. So 2 BL equals mu naught times J times L times W. L's cancel out that arbitrary width of our Amperian loops. we've got the magnetic field strength above and below this infinite slab of current. Looks like 1/2 mu naught J W. Okay, kind of an interesting result. Our B field doesn't seem to diminish with distance if our slab truly is infinite in extent. Okay, but that's on the outside. That's above and below the slab. What about inside the slab? Let's try out a similar argument here. I'll sort of start with the answer, and then we'll use Ampere's law to see if we can justify that answer. We found that B is uniform above and below by our loop argument. So let's see. I could draw sort of the magnetic field at a few locations above. This would be magnetic field vectors, there and there, pointing to the left. Once we start going inside, we'll see that magnetic field diminishing. Here's the answer, and then we're going to come to try and prove it in a bit. As we head towards the middle line of this slab, B goes to 0, and then past the middle line, B will start increasing in the other direction until we get on the outside, where B then stays constant. It's uniform, as we just showed above. So uniform B outside, then B diminishing to 0 at the center and picking up, increasing in the opposite direction on the other side, then staying constant once we're on the outside. Okay, let's see how we can use Ampere's law to prove that this is in fact the case. Okay, let's draw in that middle line and drop kind of a, let's call it the z-axis here in that picture, and draw an Amperian loop, a rectangle once again, that encloses some current. Circulate around this way. Let's say that the width, let's say that distance there is z, if here z equals 0, so this width here is 2z, and the length, the whole length we'll call L. Whole length we'll call L, so the width is 2z, length is L. Let's apply Ampere's law to that. Okay, our integral B dot ds along the bottom segment here, plus 0 for B dot ds along there, plus B dot ds along the top segment, plus 0 for that side, equals mu naught times our current enclosed. And our current enclosed will be J, the uniform current density, times the area of our Amperian loop here. So the area will be 2z times L. Okay, that's our current enclosed. All right, B at the bottom, let's say. Well, this B will be uniform along that leg, and it's in the same direction as ds, so we can pull it out and say B at the bottom and add up all the ds's to get length L, plus 0 for this segment, plus here B at the top segment times add up all the ds's gives us length L, so this is mu naught J times 2ZL. Okay, so if this Amperian loop is centered on the center line, so this is Z up here and Z down there, then by symmetry, B at the bottom should be the same as B at the top. So those are actually combinable into an expression 2 times B as a function of Z, B at some distance Z below or above the midline here, the midline where Z equals 0. So 2BZ times L is mu naught j times 2 ZL. Okay, then those 2's are going to cancel, the L's are going to cancel, and we find that B as a function of Z, distance above or below the center line inside the slab, will be mu naught J, 2 L's cancel, mu naught J Z. Apparently, B increases linearly with your distance above or below the midline. That's what I was suggesting with these magnetic field vectors here. B starts at 0 at the middle and increases linearly, gets bigger and bigger and bigger as you get further away from that midline. And then linear increase down here, then stays constant once we are outside. If we were to draw a graph of this result, let's do it right down here. Let's graph this. Let's say that this is our x direction here, so we'll graph bx, x component of b, versus z, your height above the midline or below the midline. Okay, so above the midline here, bx, it points in the negative x direction, so bx is negative above our midline. So when z equals 1/2 w, 1/2, this is negative 1/2 w, so that is down here at the bottom of the slab, plus 1/2 w, that's up here, top of the slab. So here at the top of the slab, B is pointing in the negative x direction, so B is negative down there, and we saw it increased linearly from 0 to the surface, and then stayed constant once we're outside. That constant value we showed was 1/2 mu naught JW. That's in the negative x direction. Down here on this side, as we go to negative z, B is pointing in the positive x direction. So as we go to 1/2 z, or sorry, as z goes to negative 1/2 w, bx increases in the positive x direction and then stays constant as we go down to lower and lower values of z. So this is plus 1/2 mu naught JW. And we see here that this expression for B inside agrees with this expression for B on the outside. If we set z equal to 1/2 w, we find that the two equations show that B is indeed continuous at that surface. So there's our continuous B field at the surface of our bus.